Okay, it's time to get started. The people that I don't see are Chad and Sally. So, just two announcements here. Number one, about the posters for lab. I talked to Dr. McNeil this morning. She actually tried to see if she could have them later, and the answer she got was, no, they don't have time to print them. We need to get them in by Friday. So our due time here is, I put Friday at 2:30 to me because I need to deliver them to Corain by 3. Now, Tori asked me PDF, and I think we can either use PDF or leave it in the PowerPoint. I'll check with Corain to make sure and let you know Wednesday, or actually Tuesday in lab. So we have clarification on that because I didn't think about what is the preferred option here. Concept coach, I'm not sure that I made it clear where I was going to be stopping today, but for Friday, make sure that or for Wednesday, today is Monday. It's already been a long day. Started with the trip to the dentist because I cracked a tooth yesterday. So through 31.2 for class on Wednesday. So any questions about those two things? Excellent then. Moving into the guts of the material, maybe. So the Bohr model. We looked at the Bohr model. What were the basic, I talked like 4 different things that Bohr said, okay, my model has this, 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 and this. What were the things about the Bohr model?
The orbits are quantized.
Okay, the orbits are quantized. You have what he called stationary orbits. So you only had certain orbits that were possible. Another thing?
The electrons can only exist at the orbits. They're not going to be halfway between the two.
Okay, the electrons can only exist in the energies of these stationary orbits, which means, and this is kind of a tricky thing, it means that we're going to violate electromagnetic theory. Because electromagnetic theory said that if I have a charged particle and it accelerates, that it's going to give off radiation. But if it gives off radiation, it's going to lose energy. And Bohr said they can only exist in these energies. Thank you very much. They can only exist in these energies, and so they can't continuously give off radiation. So that law of electrodynamics is thrown out by this assumption. Okay, other parts of it, what he actually quantized was angular momentum. Remember, he said that the angular momentum had to be integer multiples of that Planck's reduced constant. That was his actual quantum condition for his Bohr model. And finally, he said they do circular orbits. So putting all these together, Bohr was able to calculate an energy spectrum, and that energy spectrum was a great success because it predicted the energy levels matching those observed in hydrogen gas. So, I mean, you come up with this model, you test it, boom, nailed it. You feel pretty good about it, right? And it gave us a reason for the electrons not to collapse in the nucleus. Because if it wasn't for his condition that electrons can't radiate as they orbit, no atom would have electrons orbiting it after about a billionth of a second. So that's kind of a success. And of course it maintained, since he was working with Rutherford, he maintained what Rutherford had already learned and what before him Thomson had learned. But it wasn't perfect. There are other experiments that it failed on. And remember the whole thing about the scientific method, you come up with a hypothesis to explain something, and then you do an experiment that tests the predictions. And so here's just 2 things. There's not that many, but there are a few things where it failed. And one of them is some emission lines are brighter, stronger than others. And the Bohr model couldn't explain why this one is brighter than that one. Another thing is there is what we call fine structure. The last slide, the next last slide, has a diagram illustrating fine structure. If you look at the lines in close detail, you see that they're not exactly one line. There's multiple lines, even if you're not in a magnetic field. So that's the fine structure, and the Bohr model couldn't explain it. So if your model makes a prediction and it fails, that is, the test shows your model is wrong, then what do you do with the scientific method? You modify your explanation. So scientists got down to work to modify this and came up with what we call the quantum model for the atom. And so the quantum model for the atom is based on quantum physics, and thus it's based on probabilities. So the quantum picture is a lot different from Bohr's picture, because Bohr's picture said electrons do circular orbits. The quantum model says, well, there's a probability that the electron is here. The quantum model doesn't even say what path the electron takes. A lot of people don't have that right. A lot of people have taken general chemistry and they've learned that a p orbital looks like this, and they thus presume that the electrons do figure eights. And that is not at all what the p orbital means. The p orbital has that shape because it's talking about where you're likely to find the electron. You're likely to find the electron within the volume of that figure eight. But it's not going to be doing the figure eight as far as we know. And in fact, in the origins of quantum mechanics, there are 2 points of view, 2 approaches that were taken. Erwin Schrödinger made a wave equation. A wave equation, like we talked about, the electric field was the wave equation for light. Well, it was the wave function. And so he came up with the wave equation so you could find the wave function for the particle. So he did a wave method. But the wave method already says, well, we can't really tell you where it is. We can just tell you where the probabilities are of it being. The other approach was the one done by, actually, I think it was Heisenberg that did the other approach, where he simply said, okay, we can't know where the electron is, so forget about it. Let's not even worry about where the electron is. Let's worry about what we do know about the electron. So we can measure things like the electron's magnetic moment and its energy. And so let's just take these values and let's start categorizing and just making tables to categorize the values. And when he did his work, put it together, gave it to his advisor looked at it and knew enough to say, wow, it looks like you're doing some, I think it was, matrix methods here. So he sent it off to a mathematician who's good at matrix methods, and he cleaned it up, and we have our matrix approach to quantum physics. 2 completely different approaches. Neither can tell you where position is. One is based on just throwing up your hands and saying, I can't tell you where position is, so I'm not going to worry about it. And the other is just going with the wave nature of a particle. So probability is a big thing when we talk about the quantum model. We only have probabilities. Probabilities about what the energy will be, where the position is, and so on. There are quantized energies, but we can say, well, it's got a 60% probability of this one, 30% probability of that one. This is a common picture you see for a hydrogen atom with the quantum model. How is this different from the picture on the front page? The front page, the first slide I showed you?
Probability column.
Yeah. It's not clear. It's not on this line in a circle. It's just getting darker and brighter. Well, darker and whatever. Why? Because it has a higher probability of being like here than it does of being out here. So they made it darker where it has high probability, dimmer where it has a lower probability. So we're going to get into this to understand it. And we're going to go back to the wave function. This is what the wave function looks like for the ground state. I don't know if I've ground into you what ground state means. Ground state means the lowest possible energy state. So for the lowest possible energy state of a hydrogen atom, we call it the ground state. And this is what the wave function looks like. Now, wave function, also known as the probability density, doesn't tell you the probability of where it's going to be. How do you find the probability of where it's going to be from the wave function? Think back to light. We had the electric field that was the same as the wave function. The intensity tells us where the light is. How did the intensity relate to the electric field? Squared. So we have to take this wave function and square it to get information about where I'm going to find the electron. So here I have psi mod squared. It's actually calculated like this, where star means complex conjugate. Which means if you have an imaginary number I, you change it to a minus imaginary number I. The reason you do that is it gives you a real. It's the same idea as squaring a number. If it's a real, it's just the same as squaring. So it's called mod squared, absolute value squared. So there's the psi mod squared. That's going to give us something about probability except for one thing. The actual probability of being between r and r plus dr is going to be psi mod squared times the area of a spherical shell. Well, I'll put dV. The area of a sphere is 4 pi r squared dr. So you have the psi mod squared, and then this here is the dV. So the probability of being in some small region, I say dV, that means some uncertainty delta V in where you're looking. The probability of being in that region is given by this equation. So I have to take the psi mod squared and I have to multiply it by 4 pi r squared. And then that will give me the probability of being a distance dr away. So if I take these two lines and multiply them together, I get a graph that looks like this. And so there's my probability of being at some distance away from the nucleus. And you can see, hey, there's a peak right here. And looking at the units, this is a peak at r is equal to the Bohr radius. The quantum model gives you the most probable distance from the nucleus to the electron is equal to the Bohr radius. But it does not say that the electron is doing a circle at that radius. It doesn't say anything about its path. And it says, in fact, the electron could be here. It's just not very likely. Could be way out here. It's just not very likely. And in truth, the electron could be at the moon. It's just vanishingly unlikely. So it doesn't tell me where the electron is. It doesn't tell me how far it is from the nucleus. It just tells me where I'm likely to find it. Our first clicker question. And you can start answering now. I'm sorry I didn't have it ready. Sorry, that will make it easier. What calculation gives the probability of n? Sorry, I did not realize it wasn't on the screen. Okay. Yeah. It ain't that one. You have to have the square part. It's the psi mod squared times that 4 pi r squared dr, because the 4 pi r squared dr is the little delta V, a segment of volume for it to be in. So that's coming back to the probabilistic and how we can interpret things from quantum mechanics. Quantum numbers. We will not do the hydrogen atom in class tomorrow. We'll do the particle in the box. Because the hydrogen atom is a pretty complex calculation. And you have to do a lot of work. And in that work, it turns out that you introduce not just one quantum number, but just for the radial function, well, excuse me, it's the radial and angular functions. For the radial and angular functions, for the spatial functions, you introduce 3 quantum numbers. For spatial, I never know how to spell spatial. Now with the Bohr model, how many quantum numbers did we have? One. We had one quantum number with the Bohr model. He introduced that quantum number because that quantum number told you the angular momentum. But then when you go through your calculations, it turns out the quantum number also told you the energy. With the quantum model, we still have a number that we call n. And we call that number the principal quantum number because it principally tells us the energy. Now, other quantum numbers do affect the energy to a small amount, but the principal quantum number primarily tells you what the energy is. And it turns out, just like with the Bohr model, that the equation for energy of a hydrogen atom, it's the same equation with the same n. So at this point, once again, when I was your age, I was like, well, isn't that just the Bohr model then? I mean, the n tells me the same thing, right? It doesn't tell you the same thing because it only tells you the energy. It's the same energy equation, but it only tells you the energy. It doesn't tell you the other things. Well, it also tells you if it's in an s orbital, the most likely position, but is the same. So that looks just like the Bohr model. But let's go on. The next quantum number is the angular momentum quantum number, or orbital angular momentum quantum number, L. Now this comes mathematically. It comes out of doing the math of the quantum physics solution. But it turns out from that math that this number L tells you what the angular momentum is. Now remember, Bohr had L is equal to NH bar. That H bar is the units of angular momentum, if you will. What we have with the quantum model is the angular momentum is square root of L times L plus 1. Square root of L times L plus 1 is not an integer, right? Square root of L times L would have been an integer if L is an integer. Square root of L times L plus 1, not an integer. Times H bar, and the L values can be anywhere from 0 up to n minus 1. So if n is equal to 1, the principal quantum number has to be 1 or higher. Integers, 1 or higher. If n is equal to 1, what possible value or values can I have for L? Only 0, because it goes from 0 to 1 minus 1. If n is equal to 4, then what values could I have for L? Yeah, 3, 2, 1, 0. Okay, so the number of L's available depends on that principal quantum number, n. And the angular momenta is just the product of L, L plus 1, square rooted, and H bar. So that tells us what the total angular momentum is. Now, if I have a top and it has angular momentum is a vector. It has a direction and a magnitude. And this only tells me magnitude. It doesn't tell me direction. So our third and final spatial quantum number is going to be one that tells me the orientation of the magnetic moment. We arbitrarily define a z direction. If I put an atom in a magnetic field, I say the direction of that magnetic field is the z direction. That's how we arbitrarily come up with the z direction. And if I put that atom in a magnetic field, it's going to respond to the magnetic field based on the orientation of its magnetic moment. And so it turns out that the amount of magnetic field parallel to an external magnetic field is ml times h bar. Notice ml, that's an integer, where ml goes from minus L to plus L. Now I'm going to draw a picture here to try to illustrate this. There's actually a picture at the end of the presentation that has this as well. I have my z-axis. And I know that I have a total angular momentum that is the radius of that circle. So in my picture, this is total angular momentum L. And then I have how much angular momentum I can have in the vertical direction. And the angular momentum I can have in the vertical direction is only going to be this amount my picture doesn't do the right thing. So what happens when you draw a random picture? The problem with my picture is it would have a line right here at the top and bottom, but that's not possible. Let's consider, in this case, if this is m sub L equals 0 at the center, then this would be 1, 2, 3. If m sub L goes between minus 3 and 3, what does that tell me about L? Excellent. So that tells me L has to be 3 because m sub L goes between plus L and minus L. And so now I can look at this and I say my total angular momentum is square root of 3 times 3 plus 1, 4, times h bar. 3 times 4 is 12. What's the square root of 12? I'm asking somebody to calculate. Okay, so my total angular momentum is 3.46 h bar, and the maximum angular momentum in the z direction I can have is only 3 times h bar, because I have L sub z is equal to m sub L h bar. What does that tell you if the maximum angular momentum in the z direction is smaller than the total angular momentum? That there's some knot in the z direction. That's a really curious outcome. It's impossible to have an atom oriented so its magnetic moment is aligned with an external magnetic field. Doesn't matter what direction you make the external magnetic field, it's impossible to have them aligned. And so what we have for the possible orientations are line. We could have it oriented so that the angular momentum is in that direction, or so the angular momentum is in that direction, or that direction. But we cannot have it oriented parallel to the magnetic field, the external magnetic field. It's a bizarre outcome. What happens with the molecule when you put it in a magnetic field? It's going to precess. That is, right now I have the angular momentum shown as to the right, but it's going to go like this around your external magnetic field. That's what we call precession, where it's rotating around. So I know how much my magnetic or my angular momentum is in the z direction, and it's going to be going from X to Y for the remaining part. So that's, well, I find very interesting, very curious. So that's our third of the spatial quantum numbers. This one here is called the orbital magnetic quantum number. So we had the total angular momentum, or orbital angular momentum magnetic quantum number. Now we have the orbital magnetic quantum number. It's called magnetic because you only see its effect in a magnetic field. If you're not in a magnetic field, you don't see its effect. That's 3 spatial quantum numbers. It's not all of our quantum numbers. Everybody knows there's another one. And the other one has to do with the electron. The electron has a magnetic moment. The electron itself behaves like a tiny magnet. And that tiny magnet has a total magnetic moment of 3/2 h bar. And just like the orbital magnetic moment, the orientation cannot be aligned with an external magnetic field. So we once again define the z direction as the external magnetic field, and then the orientation can either be partially parallel to it or partially anti-parallel. Can't be parallel, can't be anti-parallel. And so we call these usually spin up and spin down. Why does it have the term spin? Because originally scientists thought the magnetic moment of the electron must be due to the electron rotating around the circle. So they said spinning, called it a spin. Well, now they're 100% convinced that's not possible, but they have the name and they stuck with it, just like EMF and many other things, displacement currents. So spin does not mean spin. It means magnetic moment. So now we have a 4th quantum number. We have these 4 total quantum numbers that are necessary to describe the state of the hydrogen atom. And so, yes, the Pauli exclusion principle is actually a quantum mechanics mathematical outcome. When you calculate the wave function, it turns out if you have 2 particles in the same atom with the same quantum numbers, your wave function is 0. The probability of that existing is 0. So the Pauli exclusion principle says, hey, the things that can't exist don't exist. So we have the Pauli exclusion principle. No 2 electrons in an atom can have the same quantum state. That is the same combination of these 4 values. Which, of course, tells us how many electrons we can add into an orbital. I believe it's a clicker question here. How many quantum numbers are required to specify the state of a hydrogen atom? And of course, this is the quantum model, not the Bohr model. Okay, I am going to have you turn to your neighbor or neighbors and discuss your answer and your reasons for it on this one.
I saw it too.
Doesn't make sense. I use the same equation in the book. So it should only be 1 electron.
Okay, let's answer again. It's open now. Okay, we did not do significantly better. Well, we did get rid of the 3 answer, which was wrong. If we go to the Bohr model, what would the answer have been for the Bohr model? For the Bohr model, it would have been 1. But for the quantum model, for the spatial calculation, there were how many quantum numbers? Okay, so there were 3 spatial. And then you had the one for the magnetic moment of the electron. So you have a total of 4, 3 spatial, and 1 for electron magnetic moment, or electron spin, to write it in 4 letters instead of 12 or whatever magnetic moment comes up to be. So you have to have those 4 quantum numbers to describe a quantum atom. Those are the principal quantum number n. Well, actually, let me just go to the next slide. Those are the principal quantum number n, the orbital angular momentum L, the orbital magnetic m sub L, m stands for magnetic, and the spin magnetic m sub s. So when you look at an electron in an atom, those are the numbers you have to look at. What is it going to naturally go to? Which energy state would an electron naturally want to be in? The lowest possible state. We call that one the ground state. So which quantum number tells you the energy primarily? N. Now I said primarily. In your level, you probably think it's always. But it's not. Yeah, it's more complicated. So N tells us the energy, and it's going to go to the lowest possible N. So that means the ground state is going to be n equals 1. But then L has to be between 0 and 1 minus n. So in the ground state, what is L going to have to be? 0. And then the orbital, if L is equal to 0, that means you have no angular momentum. So how much angular momentum do you have in the z direction? Clearly it has to be 0. But then you're left with 2 possible spin values. So in the ground state, you could have either this or this. Hence, you can put 2 electrons in the ground state because those 2 electrons have a different set of quantum numbers. Now, if you go to the first excited state, that would be n equals 2. For n equals 2, what values can L have? 0 or 1. So we could go through L equals 0 and put 2 electrons in L equals 0, but then we could also have L equals 1. If L equals 1, then I would have 3 values for m sub L, and each one of those 3 values can have 2 values for m sub S, and so you have a total of 6 electrons that can go into the n equals 2, L equals 1, and so on. So when we talk about an atom, and I'm pretty much talking about hydrogen atoms right now, but we are about to switch into talking about any atom. We talk about the shell and the subshell. The shell is the value of n. If n equals 1, that's the first shell. N equals 2, you're in the second shell, and so on. You look at the periodic table. You have the period marked there. 1, 2, 3, 4, 5, 6, 7. The period is telling you what shell you're primarily filling. Now, as I'll talk about later, it's not exactly. It tells you what shell you're filling. And then the subshells are the combination of N and L. So for the first period there, for N equals 1, we only have 2 atoms, hydrogen and helium, because you can have 2 electrons in N equals 1. Then you go to N equals 2, and if N equals 2, you can have L equals 0, which allows 2 electrons. So lithium and beryllium have electrons in the 2, and then L equals 0 has 2 electrons in those. And so it has a completed shell there at beryllium. And then if you add 1 more, then you're going to go to L equals 1, and you put 6 electrons in there. If you go to the third level, you see a flaw. Because if n equals 3, what values can you have for L? 0, 1, and 2. So we have up there, for L equals 0, sodium and magnesium. So here we have L equals 0. For L equals 1, we have aluminum through argon. Where's L equal 2? L equals 2 because n is not the only thing that tells you energy. It turns out that for L equals 2, you're at a higher energy than if you go to n equals 3, L equals 0. And so it's going to fill these two, the n equals 4, L equals 0. It'll fill these two, and then it goes back to n equals 3, L equals 2, and fills these. And then back to n equals 4, L equals 1 to fill those. So the periodic table itself tells you no. And the principal quantum number cannot be telling me the total energy. It's just the principal quantum number primarily tells me the energy. We have what we call spectroscopic notation, where we use letters for numbers. Now, it does seem kind of silly because letters and numbers are both equally easy to us. But everybody has learned things like SPDF, GH. And that is just substituting for L equals 0, S. For L equals 1, P. For L equals 2, F. Or D. Wow, nice. After P comes D, S. D. For L equals 3, F. And so on. And so it's just a straight substitution. And then we'll indicate the subshell by saying the n value, the L symbol, the symbol to tell me the L number, and then finally the number of electrons in it. And I think I have another slide that deals with this as well. Yeah, so here you have the L values, the spectroscopic notation, and the number of electrons that will fit in each one of those subshells. So like we said, we have M sub L only can be 0 for L equals 0, so we have 2 electrons, spin up, spin down. Here we can have M sub L is 3, 3 times 2 is 6. Here we have M sub L can go between -5 to +5, or excuse me, -2 to +2, which gives me 5 states. 5 times 2 is 10. The next one has 7 states, so 7 times 2 is 14. That's why we have those spacings up there on the periodic table. I want to look at the electron orbitals, and then I'm going to talk about things like Hund's rule. So, here's some pictures trying to illustrate orbitals that are not simple 1s orbitals. The 1s orbital is the simple one that I showed. And instead of staying on this, I'm going to go to that website you see, winter.group.shef.ac.uk, Sheffield University, I think it is. And their website, Orbitron. Website. There it is. That one. Okay, this website is really, really cool. I don't know, I've told the chemists many times they should use it, so I don't know if you are using it or not in your chemistry classes. But this website basically shows you what the quantum results are for basically every atomic orbital that you are familiar with. So we'll start with looking at the 1s. What does its wave function look like? Boom. It looks like that. It's symmetrical about 0, so of course this and this match. How is that useful? I showed you that in like the 4th slide today. What do we use that for? How is that useful to the quantum model? Okay, we square it and multiply it by 4 pi r squared. It tells me the probability of being in a region. So that by itself doesn't tell me really what I want to get to. It's the starting point from the calculation. This here is just squaring it. Still not done because I have to multiply by the 4 pi squared, or 4 pi r squared. And so here it's multiplied by the 4 pi r squared. And you see I showed you all 3 of those. Well, that's really not exciting. Neither is looking at the equations, if you want to be honest. Here's what the equations are like. Excited? Absolutely not. Okay, a 2s. What do you suppose a 2s looks like? A 1s was very boring. What do you suppose 2s looks like? Can you see? Okay, I'm going to turn off more lights. You have this region in here where it has nothing. Now, the way this is calculated is they're calculating where you have, X% chance of finding the particle. And so what this is saying is there's a good chance of finding it out here. There's no chance of finding it in here, and then there's a good chance of finding it in here. So you have a place where it's not likely to be found. Well, let's look at the wave function. See, the wave function goes negative and positive now. At that point where it crosses 0, psi squared is going to be 0. It's going to be no probability. The radial distribution here shows us where is it more likely to be found? Closer or farther? Farther, right. There is a local maximum probability, but this is a much higher probability. So if you were to try to find where the electron is, you could do an experiment and find, the electron is this far from the nucleus. And if you do that experiment hundreds of times, you'll start to build up how many times you found it in each distance, so it looks like this. And you'll never find it at that 0 point, even though you'll find it on both sides. Now, think about that for a second. The electron can be closer than that 0 point, it can be farther than the 0 point, but it can't be at the 0 point. How does it get from one side to another? Teleportation. The fact is, we're talking about a wave nature for the particle. When I had an electron going through a double slit, what did I tell you about the slit that it went through? It went through both at once. The electron is simultaneously in all of its allowed positions, and when you measure it, you're just going to find it in one of them. And the probability of finding it in one is what this equation is telling us. Now, that's a pretty bizarre statement, because you can't say, well, Richard is simultaneously at home and in bed and here in class, and it's just I take a measurement and I randomly found him here in class. But if I close my eyes and try again, he might be home in bed. But that's what quantum physics says. Of course, like all normal human beings, I'd rather be home in bed. Okay, so 2p, or not, what does a 2p look like? Okay, dumbbells. So let's look at the 2p. We have three orientations. Why? Because we have m sub l equals 1, 0, and minus 1. So we have three different scenarios here. Those aren't the same shape that you probably are used to seeing. Are they? These are like shorter and fatter, is the way I view it. Why is it different? They chose a different percentage for probability of it being here. So if we go to the wave function, it's anti-symmetric, but it still has symmetry, so it's anti-symmetric. The radial distribution, wow, what does that look like? Yeah, it looks like the 1s, because it is the same function as the 1s. It's not the same distance, but otherwise it's the same function. Now go to the 3s. We've seen the 2s, the 1s. What's the 3s going to look like? It's going to have two places where it can't be. So we have the center it can't be, and out here it can't be. The wave function, there you have. And of course, the all-important radial distribution. Three different places where it's most likely, of course. Out here is clearly where you're going to be expecting to find it most of the time. 3p. I'm going to go through D. What do you suppose 3p looks like? Like two people?
Yeah, like 2 people.
Okay, Okay, I misunderstood you. So here's what it looks like. To me, that looks like a doorknob. But it does indeed go to 0. The wave function you can see should look familiar. Radial distribution, two likely distances. The 3D. How many people like to write d orbitals? Yeah, nobody does, right? It's complicated. So you have 5 different orientations, so 5 different looks. One of them is clearly not like the others. If we look at the wave equation, though, they're all based on the same wave equation. The radial distribution is pretty simple, but you have that complex angular function. Okay, I'm going to go straight to 4p, just a little more complicated. 4d, you've got extra little pieces. I like these little guys in here. And an f orbital. I had students say, why are you talking about f orbitals? They don't exist. Well, sure they do. All you have to do is excite an electron, get it up into the 4 state, and you can have f orbitals. So there's what your 7 different variations of the f orbital look like. It's getting more cool, right? We can go on up to G. Here's a 5G. And if that's a 5G, then a 6G is going to be even more fun. Now, what's the point of this? It's showing where you're likely to find electrons in the different orbitals based on quantum physics calculations. A lot of you have taken chemistry. Why is this important for chemistry? This is what chemistry is based on. What'd you say, Lizzie? Get a good grade. No classes, getting a good grade is an important aspect. It's an important aspect for getting where you want to be, but not for any class.
I misunderstand college.
Okay. There is a general disconnect between students and teachers on this. Okay. When you talk about bonding in chemistry, you're talking about how orbitals combine to form a molecular orbital. And so this website also gives us diagrams of, dihydrogen. Let's first go to the sigma. What is a sigma? What do you call that?
Bonding orbital.
It's a bonding orbital. And so with the bonding orbital, we have, as the 2 hydrogens get closer together, the actual wave functions merge, and now you have a situation where the electrons are now shared between the 2 atoms, holding them together. So that's what the S looks like. What about the S star?
Isn't it like opposite on the opposite sides or something?
For the S star, that's a anti-bonding orbital. When they get closer together, instead of having the wave functions overlap, they actually repel each other, and it doesn't allow them to come together. And so the explanation of bonding and anti-bonding orbitals comes through this. And you can look at things like a sigma, this is a sigma p. A sigma p is a single bond but made with p orbitals. Or you can look at a pi. There's a pi x. And the pi y. Just looking from a different angle, really. So I really like this because it helps to illustrate what's really going on, what you're studying when you're studying chemistry. You're studying these atoms come together and their wave functions, either if they're symmetrical or, they can either overlap or repel each other. And that's the basis of bonding and chemistry in its entirety. Sadly, I'm out of time. I was going to go over the periodic table here, but we will end at this point. So, have a swell Monday. If you are interested, the prospective biology teacher is giving a lecture at 12:30, since obviously you missed her class where she was teaching right now. Becky Greer, Dr. Greer. She's a veterinarian.